Good morning. So hopefully we didn't have too much trouble yesterday with the assignment, but I do want to take a minute to kind of go over the problems that were assigned. So the first problem was this direct substitution cosine problem. So as with all limit problems, the first thing we're going to try to do is directly substitute because if we can and we get an answer, life is pretty good. Okay, so now we need to remember a unit circle, which for some of us is pretty easy and some of us struggle with a little bit. But cosine of 2 pi over 3, 2 pi over 3 is in quadrant 2, making it negative for cosine. And it's an over 3, so I believe it is 1/2. So negative 1/2 over pi over 3. Now, with a little bit of algebraic luck, we're going to we're going to flip over the fraction in the bottom and we should get negative 3 over 2 pi. And so this one turned out to be pretty easy. All you had to do is directly substitute. For letter B, we're going to try the same thing. We have 3 sine of pi over 2 squared. Sine of pi over 2, that is a 90-degree angle. So sine that's straight up is a measure of 1 unit. And so we have 3 times 1 squared, which is just going to equal 3. So both of these problems are pretty straightforward. If you have any questions on them, or if you got the unit circle, incorrect, make sure you go back and check to see what was going on. All right, the next example, I think turns out pretty well. We started with discussing what would happen if it doesn't go well on the other video. But right now, I think we're in good shape because cosine of 0 is going to be 1, so this one's going to work out pretty nicely. Sine of 0 is 0, so we've got 0 minus 1 over 1, and so our answer here is negative 1. Okay, so that kind of recaps what we did yesterday. If I scroll down to have you discovered a pattern in all of these types of problems yet, I would say the first thing we discovered is sometimes you can get a number value. Right? You can get a number by just directly substituting. Now let's take a look at example 7. Example 7, if I plug in right away, what I will see happen is I think we should be okay. I mean, cotangent of pi over 2. What is cotangent of pi over 2? Well, it's cosine over sine, right? So I could rewrite this as 2 cosine of theta times cosine of pi over sine. And so this one would have worked out had we just kind of left it alone. But I think what would have happened here is we would have gotten 0, right? So I think sometimes these trig functions are going to write us off as 0, and what we need to do is kind of rewrite them. I think it would have been okay, as long as we didn't get 0 over 0, in which case I don't believe we would have, because would have gotten 0 times 2 times 0. So this would have, direct substitution would have worked just fine. But at least you can see, or at least try to remember how to write these. Okay, and so if you don't remember, and another reason this is a good skill is if you don't really remember the cotangent and tangent of every angle. I think for the most part we're pretty good at remembering sine and cosine, but I think it's a little bit trickier if we try something else. All right, the next problem we're going to look at is sine times cosine over tangent. So sine of pi over 4 is going to be some root 2 over 2. Same thing for cosine. Tangent of pi over 4 is 1. So I believe that what happens here is we still get a rational answer. So we're going to just directly substitute here as well. I've got root 2 over 2 times root 2 over 2 over 1 Everybody's pretty positive here. So then we have the square root of times the square root of 2 times the square root of 2 over 4. So I believe this answer is 1/2. All right. The limit as theta approaches pi, we have sine. And so this one I want to like write out a little bit so we can kind of get rid of some messy stuff here. This is 1 over sine times sine. And so if I had put in cosecant here, what I would have gotten was an undefined. This would have been undefined, because you can't have 0 in the bottom, right? But now, because I'm using my Pythagorean identities, these two are going to cut and cancel, and what we would get is the limit as theta approaches pi of 1 over 3 theta, which in this case would be 1 over 3 pi. Had you directly substituted, what you would have gotten was, an undefined over a number, and that doesn't work. And so for all types of limit problems, we can certainly get a number value. That absolutely happens, and that's really nice when it does. The other thing we could have gotten was a number over 0, and then the final thing we could get is 0 over 0. And when we see in trig functions a number over 0 or 0 over 0, these are things that we might need to factor, cancel, rationalize, all of those skills that we've talked about before. And then finally, if none of those work, we look at the limits from the left and the right and see if they match. All right, so these two particular trig functions are considered 2 of the 3 special trig limits. The third is a little bit tricky. I'm going to write it on here. It's also a transcendental. These are just kind of things that you should memorize. You won't see 1 over x. This is such a weird one, but the answer is E, right? And so when you look at these, it's best that you memorize them, right? So if you see any sine of theta over theta, it's equal to 1. And if you see a 1 minus cosine of theta over theta, that is equal to 0. And so anywhere you can factor that out, that'll benefit you in the long run. I will show you how to get these when we learn L'Hopital's rule. These also could be used, great examples of squeeze theorem. It's another way to see why this works in particular. So if I look at the first example, if you guys would like to make the chart to figure this out, that's fine with me. If I were to plug 0 directly into this function, I would get 0. Okay, but the limit actually does exist. And how we find it is we write this equation as sine of theta over theta times 2, which is kind of in, against your intuition here. But every one of these you can then multiply it. The limit here happens to equal 2. In the second example, it looks an awful lot like our special trig limit. And so even if you could pull out the 3 like you did in the first example, the answer here is just going to be 0. In this example, we're going to take the ratio of the coefficients. So again, we have sine of theta over theta times 3/4. Again, this is improper mathematics, but this is how it works. This equals 1, and we have 3/4. And again, if I look at the last example, we have that 1 minus cosine over theta. Doesn't really matter what's going on. This is going to equal 0. Okay, so let me show you how the proper algebraic trick for this, right? So now we get it, right? If we see sine of theta over theta, whatever number is the coefficient, if we pull that out, that's our limit. Same thing in example C. Right? We see the 3 and the 4. It really isn't algebraically sound to move it out, but the answer turns out to be 3/4. Well, here's how it works. If I'm taking a limit of example A, I'm going to plug 0 in. When I plug 0 in, I get 0 over 0. That is called indeterminate form. In the future, when you see indeterminate form, it will indicate that you are going to take the derivative. But because you don't know derivatives yet, and we're only on limits, we're going to use some algebraic manipulation. So what I am going to do is I am going to multiply this limit by 1. It's going to be a special one in terms of 5 over 5 times sine of 5 theta over 2 theta. And I'm not actually going to, oh, there's a 3 here too. I'm not actually going to multiply that out. What I'm going to do is I'm going to rearrange some things. I'm going to make it so I have sine of 5 theta over a 5 theta. So out here to the left, I have 5 times 3 over 2 times sine of 5 theta over 5 theta. All I did was, it's commutative property of multiplication. I changed the order in which I multiplied, but it doesn't matter because you can change the order and the results are still the same. All right, so now sine of 5 theta over 5 theta turns out to be 1. And then we have 15 over 2. And so that's exactly how you're going to approach these limit problems. What I'm going to leave for you to do is to try some of these, just the ones with sine, in your homework tonight. If you have any questions, these can be pretty tricky, so reach out. I'll talk to you soon.